Hey there, how's it going? Thanks for joining me today. Whether you're relaxing at home, on your commute, or winding down for the evening, I'm really glad you're here. October 15th, 2024, 3:17 in the morning, Hawaii time. Graduate student Maria Chen sits alone in the observation room at the Maui Space Surveillance Complex, her third cup of coffee growing cold beside her keyboard. The facility is quiet at this hour, just the hum of computer fans and the occasional click of tracking systems adjusting telescope positions. For 6 hours now, she's been monitoring what appeared to be just another unremarkable space rock drifting through the outer solar system. Then the spectrometer data refreshes on her screen. Her hand jerks, knocking the coffee mug to the floor, where it shatters across the tile. She doesn't notice. She can't look away from what the computer is telling her. Before we continue this journey, tell us where you're tuning in from, and if this story resonates with you. Make sure you're subscribed, because tomorrow I've saved something extraordinary for you. The object catalogued as 3I Atlas isn't behaving like any comet humanity has ever observed. Here's what makes it extraordinary. It's traveling at 67,000 miles per hour relative to our sun. To put that in perspective, that's 3 times faster than Voyager 1, our fastest spacecraft, which has been accelerating for nearly 50 years. That velocity alone tells astronomers something profound. This object didn't form in our solar system. It came from somewhere else, somewhere beyond the gravitational influence of our sun. It's only the third confirmed interstellar visitor we've ever detected, an immigrant from the vast space between stars. But velocity isn't what made Chen's hands shake as she picked up the phone to call her supervisor at 4 in the morning. It was the chemistry. Deep within the comet's icy shell, her instruments detected something that shouldn't exist out there in the frozen darkness. Phosphine gas, mixed with complex organic molecules, in ratios and combinations that match biological processes. Here on Earth, phosphine comes from exactly 2 sources: industrial chemistry in factories or the metabolic processes of living organisms. Out there, in the void between stellar systems where temperatures hover just a few degrees above absolute zero, there are no factories, which leaves only one possibility, one explanation that changes everything we thought we understood about life in the universe. The comet itself defies every model, every prediction. Picture this. An object 2 miles wide and 7 miles long, roughly the size and shape of Manhattan Island, tumbling end over end through space. But unlike the dirty gray snowballs we're accustomed to seeing, 3I Atlas glows. An eerie blue-green luminescence pulses from somewhere within its icy structure, brightening and dimming in a precise 17-hour cycle. That's not reflected sunlight. Something inside this wanderer from the stars is generating its own energy, maintaining temperatures that instruments measure at 50 degrees Fahrenheit, warmer than the surrounding ice should physically allow. When Chen's supervisor arrived and confirmed her readings, when they verified the instruments weren't malfunctioning, when they ran the analysis 3 more times and got the same impossible results, they activated protocols that had never been used before. Emergency protocols. Within 2 hours, news reached the International Astronomical Union's headquarters in Paris. Within 4 hours, priority alerts went out to every major observatory on the planet. And within 6 hours, humanity's most powerful telescopes began pivoting toward this cosmic visitor that might, just might, be carrying passengers. The global response was unprecedented. In Chile, the Atacama Large Millimeter Array, 66 radio dishes working in perfect synchronization, detected amino acid signatures in the comet's tail. These weren't simple molecules. These were the building blocks of proteins, arranged in patterns that looked disturbingly familiar. The Keck Observatory in Hawaii, using adaptive optics to peer through Earth's atmospheric turbulence, found carbon chains arranged in structures resembling cellular membranes. Not random chemical noise, but organized complexity. Then the James Webb Space Telescope, humanity's most sophisticated eye in space, spotted something even more remarkable. Water vapor venting from specific locations on the comet's surface. Not random outgassing from solar heating, which would happen uniformly across the sun-facing side. No, these vents appeared in clusters, releasing vapor in pulses, as if something beneath the surface was consuming nutrients, producing waste, following metabolic cycles. As if something inside was breathing. Here's what's really happening when we talk about detecting life on a comet. We're not looking for little green creatures waving at our telescopes. We're looking for chemistry that breaks the rules, for molecular patterns that can't form without guidance, for processes that seem to resist entropy rather than succumb to it. Life is, at its most fundamental level, chemistry that refuses to give up, that maintains organization against the universe's tendency toward chaos. And every instrument pointed at 3I Atlas was seeing chemistry that shouldn't be organizing itself, shouldn't be maintaining complexity, shouldn't be generating heat and light in the frozen void. Dr. Sarah Johansson at MIT leads one of the analysis teams working around the clock to understand what they're seeing. Every time we rule out one explanation, she tells reporters, the data pushes us toward the conclusion nobody wants to say out loud. Not because we're afraid of being wrong, because we're afraid of being right. The phosphine detection is particularly compelling. This molecule, 3 hydrogen atoms bonded to a single phosphorus atom, is incredibly unstable in the presence of oxygen or ultraviolet radiation. In space, it should break apart almost immediately. Yet instruments detect steady concentrations in 3I Atlas's emissions, suggesting something is continuously producing it. On Earth, we find phosphine in swamps and marshes, in the digestive tracts of animals, anywhere microorganisms thrive in oxygen-poor environments. The implications are staggering, but it's the amino acids that really capture scientific attention. Life on Earth uses exactly 20 standard amino acids to build all proteins. These molecules come in mirror image versions, left-handed and right-handed, like your hands are reflections of each other. Non-biological chemistry produces both versions equally. Pure chance, 50-50 distribution. But life shows preference. Every organism on Earth uses exclusively left-handed amino acids. It's one of biology's great mysteries, this universal handedness, this shared preference that links every living thing on our planet to a common origin. The amino acids detected in 3I Atlas's vapor plumes, 73% left-handed. That's not chemistry. That's not random chance. That's the signature of biological selection, of processes that favor one form over another for functional reasons. It's smoking gun evidence, the kind of data that makes scientists lose sleep trying to find alternative explanations. The comet's 17-hour pulse cycle adds another layer of mystery. Biological organisms on Earth show rhythmic behaviors tied to their environment. Circadian rhythms, the 24-hour cycles governing sleep and metabolism, exist because life evolved on a planet that rotates every 24 hours. The 17-hour pulse suggests 3 Atlas's passengers might be responding to conditions that existed on their home world, maintaining ancient rhythms even after millions of years in the darkness between stars. Temperature measurements reveal hot spots beneath the comet's surface, concentrated in specific regions rather than distributed randomly. These warm zones cluster in patterns that statistical analysis suggests are non-random, organized. Like bacterial colonies in a petri dish, like life seeking out favorable microenvironments within the frozen matrix. Instruments detect temperature variations of 5 to 10 degrees between these warm spots and the surrounding ice, sustained over days and weeks. Radioactive decay from trace elements might provide some heat, but not in these patterns, not with this organization. The discovery timeline itself tells a story of accelerating confirmation. First detection, October 15th. Initial phosphine confirmation, October 17th. Amino acid detection, October 20th. First peer-reviewed paper proposing biological origin, October 27th. By early November, 147 scientific papers had examined the evidence from every possible angle. 143 concluded that biological processes provided the most parsimonious explanation for the observed chemistry. The remaining 4 proposed exotic non-biological mechanisms involving quantum effects or unknown physics, mechanisms that themselves would revolutionize science if confirmed. Here's the part that really makes you stop and think. If life exists on 3I Atlas, it survived a journey of unimaginable duration and brutality. The nearest star system to our sun is over 4 light-years away. At 67,000 miles per hour, that's a 70,000-year journey under the best possible circumstances. But 3I Atlas didn't come from Proxima Centauri. Chemical analysis of its ice composition, isotope ratios, and mineral content suggest an origin around Wolf 359, a red dwarf star 17 light-years away. That's a voyage lasting over 4 million years. 4 million years of absolute darkness, temperatures at 459 degrees below 0 Fahrenheit, cosmic radiation that would kill an unprotected human. In seconds, impacts from interstellar dust particles traveling at relativistic speeds. Yet something survived. Something endured conditions that make the deep ocean trenches and volcanic vents on Earth seem like comfortable vacation destinations. Something waited, dormant but not dead, patient beyond any timescale human minds can truly comprehend, until it drifted into a new solar system where curious creatures with telescopes might finally notice it. This isn't just another space discovery, another press release about distant astronomical phenomena. This is First Contact. Not the first contact of science fiction, not radio messages or visits from technologically advanced civilizations. This is first contact with the most ancient, most fundamental form of life imaginable. Life that predates human evolution by millions of years. Life that traveled between stars, not through engineering or technology, but through pure biological resilience. Life that might have seeded worlds across the galaxy, spreading from system to system on cosmic winds, turning the Milky Way into a living ecosystem rather than a lifeless desert punctuated by rare oases. The implications cascade like dominoes. If life can survive interstellar journeys, then life isn't confined to individual planets. If 3I Atlas carried biological cargo from Wolf 359 to here, then other comets must be making similar journeys constantly, a steady traffic of organic material flowing between stellar systems. If these microorganisms survive 4 million years in deep space, then Earth itself might have been seeded by similar visitors billions of years ago. The origin of life on our planet, the question that has haunted humanity since we first looked up at the stars and wondered where we came from, might have an answer that points back to those very stars. Maria Chen, the graduate student who first noticed the impossible chemistry, gave an interview 3 weeks after her discovery. "I went into astronomy because I wanted to understand the universe," she said. "I never imagined I'd be part of answering the biggest question humanity has ever asked. Are we alone? The answer appears to be no. We never were. We just didn't know how to look." The comet continues its journey through our solar system, its closest approach to Earth, scheduled for early 2025. Every day brings new observations, new data, new confirmations of the extraordinary nature of this visitor. Amateur astronomers track it with backyard telescopes. Professional observatories dedicate thousands of hours of observation time. Space agencies fast-track mission proposals to intercept it, to study it up close, perhaps even to collect samples before it sails back into the interstellar void. But regardless of what additional discoveries await, regardless of what future missions might reveal, one fact remains inescapable. On October 15th, 2024, at 3:17 in the morning Hawaii time, humanity's understanding of life in the universe changed forever. We learned we're not special, not unique, not alone. We learned that life doesn't respect planetary boundaries, that it flows through the galaxy like water through a river system, finding paths we never imagined. Surviving in environments we thought were absolutely sterile, the universe just got a lot more interesting. And somehow, despite the vast distances and impossible timescales, it got a lot smaller too. Because if microorganisms from Wolf 359 can reach Earth, if life can bridge the gaps between stars, then we're all connected in ways that transcend space and time. We're all part of something larger, something that started billions of years ago and continues today, visible if we know how to look. Present in a glowing comet that carries passengers from home to home across the cosmic ocean. Tomorrow, we'll explore how that journey began, how life could possibly survive the transit between stars, and what 4 million years in the darkness really means. But for now, let yourself sit with this revelation. Somewhere out there, riding a comet through our solar system might be the most important discovery in human history. Not gold or rare minerals or scientific curiosities. Life itself, proving that the galaxy is far more alive than we ever dared to hope. 4.2 million years ago, in a star system 17 light-years from where you're sitting right now, disaster struck. The star we call Wolf 359 erupted in a massive stellar flare, one of those violent outbursts that red dwarf stars are notorious for. Imagine the fury. Radiation equivalent to billions of hydrogen bombs, electromagnetic energy screaming outward at the speed of light. A wave of destruction that reached the third planet in that system within minutes. On that world, wherever oceans existed, water boiled into steam. Whatever atmosphere clung to the surface burned away into space. The surface itself became a hellscape of scorched rock and melting ice. But deep underground, in ancient ice caves kilometers below the devastated surface, something survived. Microorganisms, huddled together in protective biofilms, entered a state that's hard to call either life or death. Cryptobiosis, scientists call it. A kind of suspended animation where biological processes slow to nearly zero, where cells become glass-like structures that can endure almost anything, where time itself seems to stop for the organisms waiting in the darkness. These weren't the first microbes to seek refuge in those caves. They'd been there for millions of years already, descendants of surface life that had learned to survive in the planet's deep ice long before the flare. They'd adapted to darkness, to cold, to isolation. They'd become specialists at waiting, at enduring, at maintaining just enough biological function to repair damage and preserve their genetic information. Without knowing it, they'd been preparing for the journey of their existence. The stellar flare did more than sterilize the surface. Its violence ripped chunks of the dying world into space. The physics here are brutal but straightforward. When energy hits matter with enough force, when the explosion is powerful enough, pieces of the planet itself achieve escape velocity. They break free from gravity's grip and begin falling through space, following trajectories determined by the angle of ejection, the velocity achieved, and the gravitational influences of nearby objects. One of those fragments, massive beyond imagining, contained those deep ice caves. Our future Comet 3I Atlas, though it wouldn't receive that designation for over 4 million years. Picture it. A mountain of ice and rock 2 miles wide and 7 miles long, tumbling away from its parent world, carrying within its frozen heart the last survivors of an entire biosphere. Newton's laws took over. The fragment had achieved escape velocity, somewhere around 25 miles per second, fast enough to leave the red dwarf's gravity well and enter the interstellar medium. Here's what that journey really means. 42,000 centuries of absolute darkness. Not the darkness of a moonless night, where your eyes might adjust and see starlight. Not the darkness of a deep cave, where a flashlight could illuminate your surroundings. The darkness of interstellar space, where the nearest star provides less light than a candle would give you from 1,000 miles away. Where light itself becomes an abstract concept, something that once existed but no longer has meaning. The temperature in interstellar space hovers at 459 degrees below 0 Fahrenheit. That's just 14 degrees above absolute zero, the point where molecular motion essentially stops. At those temperatures, gases become liquids, liquids become solids, and the chemistry of life as we understand it simply cannot function. Water ice becomes harder than steel. Organic molecules that would normally react and change become frozen in place, their electrons locked into fixed positions, unable to form new bonds or break existing ones. Then there's the radiation. Cosmic rays, high-energy particles accelerated to nearly the speed of light by supernovae and other violent cosmic events, sleeting through space constantly. These particles carry so much energy that they can shatter atomic nuclei, break chemical bonds, scramble DNA into meaningless fragments. A human exposed to this radiation would receive a lethal dose in seconds. Cells would die, organs would fail, death would come quickly. Yet wrapped in their icy cocoon, protected by meters of frozen water and rock, the microorganisms endured. The ice itself became their shield, absorbing the radiation before it could reach the biological cargo. Water, in its frozen form, makes an excellent radiation barrier. Each cosmic ray that penetrated the outer layers lost energy, slowed down, until by the time anything reached the deep interior, the radiation had been reduced to levels the organisms could tolerate, could repair, could survive. But survival isn't the same as thriving. In cryptobiosis, these microbes existed in a state between. Their metabolism didn't stop completely. That would be death. Instead, it slowed to perhaps 1/1,000,000th of normal rates. One chemical reaction per year, where normally billions would occur per second. DNA repair mechanisms working on timescales measured in centuries rather than milliseconds. It's a strategy we see in Earth organisms, in the bacteria that survive in Antarctic ice for hundreds of thousands of years, in the seeds that germinate after millennia of dormancy, but never on this scale, never for this long. The path to Earth required cosmic choreography of impossible precision. Our comet couldn't simply travel in straight line from Wolf 359 to our solar system. It had to navigate a three-dimensional maze of gravitational influences, each one capable of altering its trajectory, each one potentially sending it careening into a star or ejecting it into the vast emptiness between galaxies. It threaded between binary star pairs where two stars orbit each other and create tidal forces that tear apart anything passing too close. It avoided the gravity wells of 16 different stellar systems along its path, each encounter a test of trajectory and velocity. Pass too close, and gravity captures you, pulling you into an orbit or sending you spiraling into the star itself. Pass too far and you drift forever in the void, never reaching another system. The comet survived passage through the Oort cloud, that spherical shell of trillions of comets surrounding our sun at distances up to 2 light-years. Any one of those objects could have collided with 3I Atlas, shattering it into fragments, ending the journey before it reached its destination. But space, despite containing so many objects, remains mostly empty. The distances are so vast that collisions, while possible, remain unlikely. 3I Atlas drifted through without incident, its trajectory barely deflected by the gravitational influence of those distant ice balls. Here's the mathematics of the journey. Distance from Wolf 359 to our solar system, 17 light-years, or about 100 trillion miles. Velocity, 67,000 miles per hour. Time equals distance divided by velocity. The answer comes out to exactly 4,186,312 years, give or take a few decades, depending on exactly when the ejection occurred and which path the comet took through the gravitational landscape. During that time, on Earth, our ancestors were just figuring out how to use fire. Homo erectus roamed Africa and Asia. The human brain was evolving, growing larger, becoming capable of abstract thought and language. Civilizations rose and fell. Ice ages came and went. Species evolved and went extinct. The entire span of recorded human history represents less than 1% of the comet's journey. Dr. Kevin Patel, an astrophysicist at Caltech who specializes in interstellar dynamics, calculated the odds against this successful journey. His paper, published in Nature just weeks after 3I Atlas's discovery, presents numbers that make your head spin. The probability that a fragment ejected from Wolf 359 would happen to be aimed toward our solar system, 1 in several billion. The probability it would maintain the right velocity, neither too fast to be captured nor too slow to arrive, 1 in several thousand. The probability it would avoid collisions and gravitational disruptions, 1 in several million. Multiply those probabilities together, and you get 1 chance in 700 trillion. Those odds are so small they seem impossible. Yet here it is. The comet exists. The journey happened, and that's the point that changes everything about how we think about life in the universe. When odds are 1 in 700 trillion, but the universe contains 200 billion trillion stars, with planets around most of them. With asteroid impacts and stellar flares ejecting material constantly, then even the impossible becomes inevitable. Not just possible, inevitable. The universe is so large, time is so long, that 1 in a trillion events happen thousands of times per day somewhere. If one biological package can make this journey successfully, how many others are out there right now? How many comets are sailing between stars at this very moment, carrying dormant life from system to system? How many have already passed through our solar system undetected because we weren't looking, because we didn't have the instruments, because they passed during the billions of years before humans evolved? The implications start cascading. If interstellar travel via natural processes is possible, then life isn't confined to its planet of origin. Impacts and explosions constantly eject material into space. Some fraction of that material carries microorganisms. Some fraction of those microbes survives the ejection. Some fraction ends up on trajectories toward other star systems. And some tiny fraction of those actually completes the journey. But tiny fraction across billions of years and trillions of opportunities adds up to certainty. Life spreads. Not quickly, not efficiently, but inexorably. Like seeds from a dandelion, scattered on cosmic winds, most going nowhere, but some finding purchase in new soil, taking root, beginning the process again. Earth itself may be part of this network. 4 billion years ago, during the late heavy bombardment, our planet suffered through millions of asteroid and comet impacts. Material from Mars reached Earth, and material from Earth reached Mars. We found meteorites from Mars on Earth, and almost certainly there are meteorites from Earth on Mars. Did they carry passengers? Did life spread between planets in our own solar system through natural bombardment? Some scientists suggest Earth's life might have originated elsewhere, arriving aboard an impact from Mars or from an interstellar visitor we'll never identify. It's a provocative idea, though it doesn't answer the ultimate question. It just moves the origin of life from Earth to somewhere else. But it does suggest that life's emergence, wherever it first occurred, wasn't the end of the story. It was the beginning of an expansion that continues today. The microorganisms on 3I Atlas, if that's what they are, represent something profound. They're not just survivors. They're pioneers, explorers, colonists, not through any choice or awareness. They don't have nervous systems or consciousness, but through the simple act of enduring, of maintaining the spark of biological organization through impossible circumstances. They've become living bridges between worlds. Think about what that means for our understanding of the galaxy. Instead of isolated oases of life separated by sterile voids, we might live in an ecosystem. A cosmic ecosystem where life flows from star to star, where every system exchanges biological material with its neighbors, where the emergence of life anywhere eventually means life everywhere conditions allow. The waiting period inside the comet staggers the imagination. 4 million years of silence, of cold, of stillness. On human timescales, that's incomprehensible. But for organisms in cryptobiosis, time has no meaning. They don't experience the passage of years. They don't wait consciously. They simply exist in a state where waiting and not waiting are the same thing, where 4 million years passes in what might as well be an instant until something changes. until the comet drifts into a new solar system, approaches a star, and warmth begins penetrating the outer layers of ice, until frozen water begins sublimating, creating tiny pockets of liquid lasting microseconds at a time, until dormant repair mechanisms activate, fix accumulated damage, prepare for the possibility of returning to full metabolic function, until life, patient beyond all understanding, senses the opportunity to awaken. That awakening may not have fully occurred yet. The organisms might still be mostly dormant, just beginning to stir as 3I Atlas approaches the inner solar system. But the signs are there: the phosphine production, the amino acid emissions, the 17-hour metabolic rhythm. Life recognizing, at some fundamental biochemical level, that the journey might finally be ending, that a new home might be within reach. Whether these particular microorganisms will find that home, whether they'll somehow seed Earth or another planet in our system, remains unknown. But the fact that they survived the journey at all proves the concept. Life can cross the interstellar void. Life can endure for timescales that dwarf the existence of species and civilizations. Life can wait and endure and persist until opportunity arrives. The very existence of 3I Atlas transforms the Drake equation, that famous formula estimating the number of communicative civilizations in our galaxy. But forget civilizations for a moment. The comet suggests we need a simpler equation. How many star systems harbor life of any kind? And if the answer is that life spreads naturally between systems, then the answer might be most of them, given enough time. We're not looking at a galaxy where life is rare, precious, isolated. We're looking at a galaxy where life is the rule, not the exception, where it emerges, spreads, diversifies, fills every available niche, where the question isn't, is there life out there, but how could there not be? 4.2 million years, 100 trillion miles, impossible odds overcome through nothing more than patience and the fundamental resilience of biological organization. That's the journey 3I Atlas represents. That's the story written in its ice and its chemistry and its eerie blue-green glow. Tomorrow, we'll look at exactly how life manages these impossible feats of survival. We'll meet the organisms on Earth that show us what's possible, that demonstrate how biology can overcome seemingly insurmountable challenges. We'll explore the science of cryptobiosis and radiation resistance, and all the tricks life has evolved to persist in the face of extinction. But tonight, let yourself marvel at the journey, at the sheer audacity of life crossing the void between stars, at the patience measured not in years or centuries, but in millennia and epochs, at the fact that you're living in a moment when humanity finally has the tools to detect these cosmic voyages, to read the stories written in their chemistry, to understand that we're part of something much larger than one planet, one star, one isolated bubble of biology in an empty universe. The universe isn't empty. It's alive, and the proof is tumbling through our solar system right now, carrying passengers from a world that died before humans learned to walk upright. Meet Deinococcus radiodurans. The name sounds like something from a science fiction movie, but this microscopic organism is very real, very much alive, and living right here on Earth. Scientists call it Conan the Bacterium because of its superhero-like abilities. It survives radiation doses 3,000 times what would kill a human being. Freeze it in liquid nitrogen at temperatures of 321 degrees below 0 Fahrenheit for years, then thaw it out and it wakes up hungry, ready to reproduce. Dehydrate it completely, reduce it to dust, store it in a vacuum for decades, add water, and within hours it starts dividing again as if nothing happened. This little organism isn't unique in its resilience. It's just the most studied example of a growing catalogue of extremophiles, organisms that thrive in conditions we once thought were absolutely incompatible with life. And it's our blueprint, our Rosetta Stone, for understanding how life could possibly survive on something like 3I Atlas during its multi-million-year journey between stars. Here's what makes these organisms so extraordinary. At the molecular level, they've evolved mechanisms that seem almost like they were engineered specifically for space travel, though of course they evolved right here on Earth in response to terrestrial challenges. Deinococcus radiodurans produces special proteins that wrap around its DNA like molecular armor, protecting the genetic code from radiation damage. When damage does occur, and it does constantly, the organism can repair its own genome even when it's been shattered into hundreds of fragments. It's like having a jigsaw puzzle blown apart and then watching it reassemble itself perfectly, piece by piece. The process is remarkable. The bacterium maintains multiple copies of its genome, usually 4 to 10 complete sets of its genetic instructions. When radiation breaks one copy, the repair machinery uses the intact copies as templates, copying information back and forth until all the damage is fixed. It's redundancy taken to an extreme. Imagine if your computer kept 10 backup copies of every file, updating them constantly so that even if 9 copies were corrupted, the system could reconstruct everything perfectly from the 10th. But radiation resistance is just the beginning. These organisms also create antifreeze compounds, complex proteins and sugars that prevent ice crystals from forming inside their cells. Ice crystals are deadly to most life because they grow like knives, puncturing cell membranes and shredding internal structures. The antifreeze compounds don't prevent freezing entirely. That would require too much energy. Instead, they control how ice forms, encouraging small, harmless crystals instead of large, destructive ones. Other extremophiles show us different survival strategies. Tardigrades, those microscopic water bears that look like 8-legged potatoes under a microscope, can survive the vacuum of space, temperatures near absolute zero, pressures 6 times greater than the deepest ocean trenches, and radiation doses that would sterilize any spacecraft. They do this by entering a state called ton formation, where they expel almost all water from their bodies, curl up into a ball, and produce massive amounts of protective proteins that essentially turn their cells into glass. That last detail is crucial. Glass is stable. Glass doesn't change. Glass can last for millions of years without degrading. By converting their cellular contents into a glass-like state, these organisms essentially become biological time capsules, unchanged by time, waiting for conditions favorable enough to rehydrate and return to active life. Now apply these known, observed, documented abilities to the environment inside 3I Atlas. The comet's interior isn't as harsh as open space. The outer layers of ice and rock provide shielding. Temperature measurements suggest the deep interior maintains relatively stable conditions around -300 degrees Fahrenheit. That's still incredibly cold by human standards, but it's practically tropical compared to the -459 degrees of open interstellar space. Radioactive decay from trace elements, uranium, thorium, potassium-40, provides gentle warmth. Not much, just a few watts of heat spread throughout the comet's mass, but enough to maintain those slightly warmer temperatures. More importantly, that radioactive decay creates local hotspots, tiny regions where chemical reactions can occur, where frozen water might briefly become liquid for microseconds at a time. Those microseconds matter. In liquid water, dormant organisms can briefly activate their repair mechanisms. Broken DNA gets fixed. Damaged proteins get replaced. Cellular machinery performs quick maintenance before the water refreezes. It's like a car engine that only runs for a split second every few years, just long enough to circulate oil, prevent rust, maintain basic integrity before shutting down again. Over millions of years, those split seconds add up to enough activity to prevent irreversible decay. Chemical reactions between minerals and ice create additional opportunities. When certain minerals come into contact with ice, they catalyze reactions that produce tiny amounts of chemical energy. Organisms embedded in the ice near these minerals can tap into that energy, using it to power essential maintenance processes. It's not enough energy to support active metabolism, to allow growth or reproduction. but it's enough to maintain basic cellular integrity, to keep the biological machinery from falling apart completely. Laboratory experiments prove these concepts aren't just theoretical speculation. In 2008, Russian scientists sealed bacteria inside artificial meteorites, chunks of rock designed to simulate the composition and structure of real space debris. They launched these artificial meteorites aboard the International Space Station and exposed them to the vacuum of space, to unfiltered solar radiation, to temperature swings from positive 250 degrees in sunlight to negative 250 degrees in shadow. 18 months later, they retrieved the samples and brought them back to Earth. The results startled everyone. 30% of the bacteria survived. Not just survived, thrived after rehydration. They resumed normal metabolism within hours, began reproducing within days, showed no signs of genetic damage or reduced fitness. 18 months of space exposure. Conditions far harsher than the protected interior of a comet, and nearly a third of the organisms came through it successfully. Japanese researchers conducted different experiments focusing on long-term deep freeze survival. They took microorganisms from Antarctic ice and froze them at temperatures matching those predicted for 3I Atlas's interior. Then they waited, not for years but for over a decade. 10 years of continuous freezing at negative 300 degrees Fahrenheit. When they finally thawed the samples, they discovered something remarkable. Not only did the organisms survive, they showed signs of slow metabolism throughout their frozen period. DNA repair continued at rates perhaps 1,000,000 times slower than normal, but it continued. The organisms weren't completely dormant. They were maintaining themselves, slowly but steadily, throughout the entire decade. Scale that up. If organisms can maintain themselves for 10 years in laboratory freezers, why not for 1,000 years? For 10,000? For 1,000,000? The energy requirements are minimal. The repair mechanisms are passive, driven by molecular recognition rather than active cellular processes. Time becomes irrelevant when metabolism slows to geological timescales, but the most compelling evidence comes from analysis of 3I Atlas itself, from that smoking gun that Dr. Sarah Johansson at MIT discovered in the vapor plumes. Chirality, the concept seems abstract until you understand what it means. Many organic molecules exist in mirror image forms, like your left and right hands are reflections of each other. These forms have identical chemical formulas, identical atomic composition, but their three-dimensional structures are reversed. When you synthesize amino acids in a laboratory through purely chemical processes without biological involvement, you get equal amounts of both mirror image forms, 50% left-handed, 50% right-handed. Pure chance, pure statistics, pure chemistry following the laws of thermodynamics. There's no reason for one form to be favored over the other, so you get both equally. Life, however, shows profound bias. Every organism on Earth, from bacteria to blue whales, uses exclusively left-handed amino acids in its proteins. Not 99% left-handed, not mostly left-handed, 100% left-handed, with right-handed amino acids actively rejected by the cellular machinery that builds proteins. This universal preference is one of the deepest mysteries in biology, a signature that links all earthly life to a common origin billions of years ago. The amino acids detected in 3I Atlas's vapor plumes are 73% left-handed, not 50-50 like pure chemistry would produce, not 100% like Earth's biology, 73%. Suggesting biological processes that show preference for left-handed forms but haven't achieved complete selectivity. It's exactly what you'd expect from an independent origin of life, one that evolved its own preferences through its own history, making similar choices to Earth's biology but not identical ones. That single measurement, that 23% deviation from pure chemistry, represents stronger evidence for extraterrestrial life than anything humanity has previously discovered. It's not a maybe, not possibly, not a could be. It's chemistry that cannot be explained without invoking biology. Non-living processes don't produce these ratios? There's no known mechanism, no exotic physics, no unusual chemical pathway that yields 73% of one chirality and 27% of the other. Additional evidence comes from the molecular complexity detected in the comet's emissions. Simple organic molecules, methane, ethanol, formaldehyde, form naturally in space all the time. We see them in molecular clouds, in protoplanetary disks, in the atmospheres of gas giants. But complex molecules, chains of dozens or hundreds of atoms arranged in specific patterns, those require either biological processes or conditions far more energetic than anything that exists in the quiet darkness of interstellar space. Atlas's emissions include tetrapyrroles, the molecular structures found in chlorophyll and hemoglobin. They include phospholipids, the molecules that form cell membranes, creating the boundary between life and non-life. Most remarkably, instruments have detected fragments that appear to be RNA, ribonucleic acid, one of life's fundamental information storage molecules. RNA is particularly significant because many scientists believe it was the first information molecule, predating DNA, capable of both storing genetic information and catalyzing chemical reactions. An RNA world, where RNA filled the roles now divided between DNA and proteins, might have existed on early Earth and might still exist in ancient microorganisms. Finding RNA-like molecules in a comet suggests life at a very fundamental, perhaps very ancient level of organization. The temperature profile of the comet adds another layer of evidence. The 17-hour cycle of brightening and dimming correlates with temperature fluctuations in specific regions of the comet's interior. These hotspots aren't randomly distributed. Statistical analysis shows clustering patterns, regions where warm zones appear in groups rather than scattered uniformly throughout the ice. Clustering suggests organization. It suggests that whatever creates these warm zones, whether biological heat generation or concentration of radioactive materials near organisms, occurs preferentially in certain environments. Think of bacterial colonies in a petri dish, how they grow in patches and clusters because bacteria release chemical signals that attract more bacteria, creating positive feedback loops. The hotspot distribution in 3I Atlas shows similar patterns, similar clustering coefficients, similar fractal dimensions. Here's the truly remarkable part. Life on Earth has been preparing for space travel since it first evolved. The mechanisms that allow Deinococcus radiodurans to survive radiation evolved to handle radioactive elements in Earth's crust. The antifreeze proteins that protect organisms from ice crystal damage evolved to survive Antarctic winters. The cryptobiosis that lets tardigrades endure complete dehydration evolved to survive temporary droughts in pond water. None of these organisms evolved their abilities for space travel. They evolved them for terrestrial challenges, but by coincidence, or perhaps by the fundamental nature of what life must be able to do to persist in a dynamic universe, the abilities needed to survive on Earth under extreme conditions are exactly the abilities needed to survive. Interstellar journeys. This means life doesn't need to be exotic or alien to cross between stars. It just needs to be tough. And toughness is something life excels at. 4 billion years of evolution on Earth hasn't just created delicate organisms dependent on narrow environmental ranges. It's also created survivors, organisms that can handle anything the universe throws at them, that treat conditions we consider lethal as minor inconveniences. If Earth's extremophiles can survive laboratory simulations of space conditions, if they can endure 18 months on the International Space Station, if they can remain viable for decades in Antarctic ice, then there's no reason to doubt they could survive inside a comet for millions of years. The physics works, the chemistry works, the biology works, and if Earth's organisms can do it, then so can organisms from other worlds. Life, it turns out, isn't fragile. It's not delicate. It's not rare. It's the universe's most persistent phenomenon, evolving strategies to survive in every conceivable environment. From volcanic vents to nuclear reactors to the frozen hearts of comets sailing between stars. Give life a foothold anywhere, in a warm tide pool, in a hydrothermal vent, in an underground aquifer, in a comet's interior, and it adapts. It endures, it waits. It survives conditions that would destroy steel and stone, conditions that seem absolutely incompatible with anything we'd recognize as life. And then, when opportunity arrives, when conditions improve even slightly, it awakens and begins the ancient processes of metabolism, repair, growth, and reproduction. Atlas proves the concept. Life can cross the void. Life can survive the impossible. Life can wait longer than continents exist, longer than species persist, longer than civilizations endure. And that changes everything about how we understand the distribution of life throughout the galaxy. The first hint that 3I Atlas was extraordinary came from someone you've probably never heard of. Peter Williams, a retired electrical engineer living in Christchurch, New Zealand, spends his evenings doing what thousands of amateur astronomers do, scanning the night sky with a backyard telescope, cataloging objects, contributing observations to online databases. On October 12th, 2024, 3 days before Maria Chen's discovery at the Maui facility, Williams noticed something odd. The object that would become 3I Atlas was pulsing. Not randomly, not erratically, but with a precise rhythm, brightening and dimming every 17 hours like clockwork. Williams documented the pattern, time-stamped his observations, and posted them to an astronomy forum with the subject line, "Weird periodic brightness variation in newly catalogued object." He figured it was probably instrumental error, maybe atmospheric interference, certainly not anything important. He went to bed thinking nothing more about it, but Dr. Jennifer Park, a postdoctoral researcher at Caltech, saw that forum post during her morning coffee 2 days later. She'd been tracking the same object, had noticed the same pattern, but assumed her own instruments were glitching. Seeing Williams's independent confirmation made her stop mid-sip. 2 different observers, different hemispheres, different equipment, same result. That 17-hour pulse wasn't error. It was real. That regular pulse, too perfect to be random outgassing from solar heating, too consistent to be tumbling motion reflecting sunlight, suggested something else. Internal processes, biological rhythms, the kind of cyclic behavior that living systems show when they maintain metabolic patterns tied to their environment. Williams's amateur observation, shared freely on a public forum, became one of the first pieces of evidence that 3I Atlas might harbor life. This is how modern astronomy works. It's not just professionals with billion-dollar instruments. It's a global network of observers, amateur and professional, sharing data in real time, building a complete picture from thousands of individual observations. Williams's contribution proved as crucial as any made by the major observatories. And once professional astronomers realized what they might be looking at, they deployed every tool humanity has built for studying the cosmos. The Atacama Large Millimeter Array sits on the Chajnantor Plateau in Chile, 5,000 meters above sea level. Up there the air is so thin that workers need supplemental oxygen. The altitude matters because it puts the observatory above 40% of Earth's atmosphere, above most of the water vapor that absorbs the millimeter wavelength radio waves the array detects. 66 radio dishes, each 12 meters across, work together as a single giant telescope through a technique called interferometry. When the 3I Atlas investigation began, ALMA pivoted immediately. Priority 1 observation status, meaning all other projects got postponed. The array focused on the comet for 72 continuous hours, collecting data on molecular emissions from the vapor plumes. What they found reads like a shopping list of biological building blocks, phospholipids. These molecules form the membranes that surround cells, creating the boundary between a living thing and its environment. They're complex structures with a water-loving head and water-repelling tails that naturally arrange themselves into double layers, the basic structure of all cell membranes. Non-biological chemistry doesn't produce phospholipids. They're too specific, too organized, too functional. Tetrapyrroles. On Earth, these molecules form the core of chlorophyll, which captures light energy in plants, and heme groups, which carry oxygen in blood. They're ring-shaped structures with a metal atom at the center, magnesium in chlorophyll, iron in hemoglobin. Finding them in space isn't impossible. Simple versions form in molecular clouds. But the specific variants ALMA detected match the ones produced by biological systems, not by random chemistry. Most shocking, fragments of what appeared to be ribonucleic acid, RNA, the molecule that stores genetic information, catalyzes chemical reactions, and may have been the first form of life on Earth billions of years ago. The fragments were short, just a dozen or so nucleotides, but their structure was unmistakable. The sugar-phosphate backbone, the nitrogenous bases, the specific chemical bonds that hold RNA together. The investigation reads like a cosmic detective story, with each telescope providing another clue. The Infrared Space Observatory, operating in wavelengths invisible to human eyes, mapped temperature variations across the comet's surface. Hotspots appeared beneath the icy shell, clustered in patterns rather than distributed randomly. Some regions glowed 30 to 40 degrees warmer than their surroundings, not much by Earth standards, but enormous differences for an object that should be uniformly frozen. Those hotspots showed temporal variation too. They brightened and dimmed in correlation with the 17-hour pulse that Peter Williams first noticed. Something inside the comet was generating heat cyclically, maintaining rhythms that suggested metabolic processes. The infrared maps showed clustering patterns that statistical analysis compared to bacterial colonies, growing in nutrient-rich environments, patches, and clumps rather than uniform. Distribution, the Chandra X-ray Observatory, added another piece to the puzzle. X-rays reveal high-energy processes, places where matter undergoes violent or energetic interactions. Chandra detected X-ray emissions from specific locations on the comet's surface, emissions that corresponded to the hotspots identified by infrared observations. The X-ray spectra showed element ratios characteristic of biological mineral deposits, the kind that form when microorganisms concentrate certain elements as part of their metabolism. Radio emissions provided yet another clue. The Very Large Array in New Mexico, 27 radio dishes spread across the desert in a Y-shaped configuration, detected complex carbon chains in the comet's emissions. Not simple molecules like methane or ethanol, but long chains of dozens of carbon atoms bonded in specific patterns. These chains resembled the lipids that make up cell walls, the fatty acids that store energy, the organic polymers that serve structural roles in living cells. Dr. Lisa Park leads the analysis team at Johns Hopkins Applied Physics Laboratory. Her background is in astrobiology, the study of life in the universe, but until 3I Atlas, most of her work had been theoretical. Planning future missions to Europa or Enceladus, designing instruments to detect biosignatures on Mars, modeling what alien biochemistry might look like. Now she oversees teams working around the clock, comparing the comet's chemical signatures to every known biological and non-biological process. Every test we run, she explains in a press conference 3 weeks after the discovery, but pushes us toward the same conclusion. We keep trying to find alternative explanations. We look for exotic chemical pathways, unusual physics, anything that could produce these signatures without invoking life. And we come up empty. The simplest explanation, the one that requires the fewest assumptions, is that something alive is driving this chemistry. The confirmation process follows strict protocols established long before 3I Atlas appeared. Each detection requires independent verification by 3 separate facilities using different instruments and methodologies. Data undergoes peer review by competing teams specifically trying to find flaws, errors, alternative interpretations. The process is adversarial by design, meant to catch mistakes, to prevent false positives, to ensure that any claim of extraterrestrial life survives the harshest scrutiny science can provide. So far, 147 peer-reviewed papers have examined the evidence. Independent teams from universities and research institutions across 23 countries have analyzed the data. 143 papers conclude that biological processes provide the most parsimonious explanation for the observed chemistry. That's 97% scientific consensus, higher than the consensus on human-caused climate change, higher than the consensus that smoking causes cancer. The remaining 4 papers propose alternative mechanisms. One suggests exotic catalytic processes involving quantum tunneling in ice crystals. Another invokes plasma physics in ways that would themselves represent revolutionary discoveries. A third proposes previously unknown photochemistry driven by cosmic rays. The fourth admits it cannot explain the observations, but argues for caution before accepting the biological hypothesis. These dissenting papers are important. Science advances through skepticism, through demanding extraordinary evidence for extraordinary claims. But as Dr. Park notes, even the dissenting papers don't dispute the data. They dispute the interpretation. They propose alternatives that would require new physics or chemistry even more exotic than the idea of interstellar microorganisms. Sometimes the simplest explanation really is correct. Amateur astronomers continue playing a crucial role in the investigation. Peter Williams's initial observation inspired others. Within days, a network of 3,000 backyard scientists across 6 continents began coordinating observations. They call themselves the 3i Watch Network. Every night, somewhere on Earth, dozens of telescopes track the comet, noting every brightness change, every vapor emission, every subtle color shift. Their combined data revealed patterns the professional observatories missed. The emissions don't occur randomly. They increase when certain parts of the comet face the sun, as if dormant organisms briefly wake in the relative warmth before falling back to sleep. Specific regions of the comet's surface show higher activity levels, suggesting that life, if that's what it is, isn't uniformly distributed, but concentrated in more favorable microenvironments. The amateur network also caught something unexpected. On November 3rd, the comet emitted a bright flash lasting 3 seconds. Professional instruments missed it. They weren't looking at that moment. But 17 amateur observers recorded it simultaneously. Analysis of their images suggests a sudden venting event, possibly a pocket of gas under pressure, finding a weak point in the ice and explosive decompressing. The gas composition showed higher concentrations of biological molecules than typical emissions, suggesting the vent came from a region rich in organic material. Here's what makes this investigation different from anything humanity has attempted before. We're not studying fossils, not examining ancient chemical traces, not trying to reconstruct what life might have been like billions of years ago. We're potentially studying living organisms, active right now, maintaining themselves, metabolizing, producing waste, showing all the hallmarks of biology in real time. If the interpretation is correct, this isn't paleontology. It's xenobiology, the study of truly alien life forms. The philosophical implications keep scientists awake at night. If we confirm life on 3i Atlas, it won't be life we visited, life we traveled to see. It will be life that came to us. First contact on their terms, not ours. Microorganisms that have existed longer than human civilization, that traveled farther than any human-made object will travel for centuries, that survived conditions no human could endure. Dr. Park's team prepared a report for the International Astronomical Union summarizing the evidence. The document runs to 312 pages, including detailed spectroscopic analysis, statistical evaluations, comparison studies, and proposed future observations. The conclusion section, normally dry and technical, includes this remarkable statement. Based on the totality of available evidence, including but not limited to chiral selectivity in amino acids, complex organic molecule detection, cyclic emission patterns, thermal anomalies, and the absence of plausible abiotic mechanisms capable of producing the observed signatures. We conclude with high confidence, greater than 95% probability, that object 3I Atlas harbors biological material consistent with active or recently active microbial life. High confidence. Greater than 95% probability. In scientific language, that's as close to certainty as you can get without absolutely definitive proof. It's the same confidence level scientists use when they say smoking causes cancer. The plate tectonics shapes continents, that evolution explains the diversity of life on Earth. The smoking gun, the one piece of evidence that tips the scales from possible to probable, remains the chirality measurement. That 73% left-handed preference in amino acids. Every attempt to explain it through non-biological mechanisms has failed. Every simulation, every proposed chemical pathway, every alternative hypothesis produces predictions that don't match the observations. Unless someone discovers entirely new chemistry, unless our understanding of how molecules behave in extreme cold needs complete revision, the amino acid chirality can only mean one thing: biology, life, organisms that, like Earth's life, show preference for one mirror image form of molecules over another. Not perfect preference, not 100% selectivity, but strong enough preference to prove that something is making choices. Something is selecting, something is alive. Tomorrow, we'll explore what this discovery means for humanity's place in the universe. We'll look at how it changes our understanding of biology, evolution, and the prevalence of life throughout the galaxy. We'll examine the implications for religion, philosophy, and our future as a spacefaring civilization. But tonight, appreciate the detective work, the global collaboration, amateur and professional, the sophisticated instruments and careful analysis, the rigorous peer review and healthy skepticism. Humanity at its best, working together to answer one of our oldest and deepest questions. Are we alone? The evidence suggests we never were. We just didn't know how to look. And now that we do, now that we've found one example of life crossing between stars, the question becomes, how many more are out there? How often does this happen? How many times has Earth been visited by similar cosmic travelers, carrying passengers from distant worlds? The universe just revealed one of its secrets. And like all good secrets, it raises more questions than it answers. Questions we'll spend the next decades, perhaps centuries, working to resolve. Questions that transform humanity from isolated islanders into citizens of a living galaxy. If 3I Atlas harbors life, then everything changes. Not just in astronomy or biology, but in how humanity understands itself, its place in the cosmos, and its future. We're not special anymore. We're not unique. We're not alone. Earth becomes just one island in an archipelago of living worlds, connected by cometary bridges spanning the darkness between stars. The implications ripple outward, like waves from a stone dropped in still water, touching every aspect of human thought and culture. Consider what changes in the most fundamental ways. Biology textbooks, the ones students study in high schools and universities around the world, need new chapters. Not just footnotes or appendices, but entire sections dedicated to non-terrestrial life forms. The definition of life itself might require expansion. Everything we know about biology comes from studying one example, one family tree, life that all descends from a single origin on Earth 4 billion years ago. If 3I Atlas carries organisms with a different origin, a different evolutionary history, even slightly different biochemistry, then biology transforms from the study of life to the study of Earth's life, a subset of something much larger. The Drake equation, that famous formula estimating the number of communicative civilizations in our galaxy, requires radical revision. Astronomer Frank Drake proposed it in 1961 as a way to structure thinking about extraterrestrial intelligence. The equation multiplies together factors like the rate of star formation, the fraction of stars with planets, the number of planets suitable for life, and the fraction where life actually emerges. Each factor represented a guess, an estimate based on limited data and optimistic assumptions. But 3i Atlas changes the fundamental assumptions. The equation asks, what fraction of suitable planets develop life? Treating each world as an isolated system where life either emerges spontaneously or doesn't. If life travels between stars, if comets constantly deliver biological material to every planetary system, then the question isn't whether life emerges, but whether it arrives. And arrival, given enough time and enough cometary visitors, becomes nearly inevitable. Dr. Carl Anderson at Stanford spent 6 weeks after the 3i Atlas discovery recalculating the Drake equation under the assumption of panspermia, life spreading between worlds. His new model doesn't ask about independent origins of life. It asks about the distribution of life through natural transfer mechanisms. The math becomes simpler and the results more optimistic, or perhaps alarming, depending on your perspective. If life can survive interstellar journeys, Anderson explains, and such journeys happen regularly through natural ejection of material from planets, then life should be everywhere conditions allow. We're not looking at a galaxy where a few lucky worlds independently generate biology. We're looking at a galaxy where life is the rule, not the exception. His models suggest that every star system experiences biological visitation every few million years on average. Some visitors carry dormant microorganisms. Some carry only complex organic molecules. Some carry nothing but rocks and ice. But over billions of years, the cumulative effect ensures that any world with liquid water, stable chemistry, and moderate radiation levels receives regular deliveries of biological material from elsewhere. Earth itself almost certainly benefited from this cosmic seeding. The late heavy bombardment, that period 4 billion years ago when the inner solar system suffered through a storm of asteroid and comet impacts, delivered thousands of tons of organic compounds. Some impactors came from within our solar system, material from Mars or the asteroid belt. But some, perhaps many, came from beyond, visitors from other stellar systems carrying organic cargo. Did those early visitors deliver the first life to Earth? Did they supplement native chemistry with exotic molecules that jump-started biological evolution? Or did life emerge independently here and then receive genetic diversity from elsewhere, interbreeding with alien microorganisms to create hybrid lineages? We don't know yet. But 3i Atlas proves the delivery mechanism exists, has existed for billions of years, operates constantly across the galaxy. The religious implications spark intense debate and deep reflection. Father Miguel Santos, who works at the Vatican Observatory, one of the oldest astronomical research institutions in the world, gave a carefully worded statement 3 weeks after the discovery. God's creation extends beyond Earth. This discovery doesn't diminish the divine. It enlarges our conception of divine creativity. If God placed life throughout the universe, using natural mechanisms like comets to spread it from world to world, that speaks to infinite power and infinite subtlety. Buddhist teachers find different meaning in the same discovery. Thich Nhat Hanh, a prominent Buddhist monk, notes that Buddhism has always taught interconnectedness, the idea that nothing exists in isolation, that all things depend on all other things. Life traveling between stars confirms what we have always known, he says. Separation is illusion. Connection is reality. The microorganisms on the comet and the microorganisms in our bodies share the same cosmic journey. Indigenous peoples point to ancient stories that suddenly seem less metaphorical. Many cultures have origin myths involving life descending from the sky, ancestors arriving from the stars, cosmic eggs that hatch to create the first humans. Western science dismissed these stories as primitive attempts to explain what ancient peoples couldn't understand. But perhaps they preserved some dim racial memory of an actual event, an actual arrival. preserved through generations of oral tradition. The discovery transforms humanity's future plans in concrete, immediate ways. NASA fast-tracks the Comet Intercept mission, originally scheduled for the late 2030s, moving the launch window to December 28. The mission profile involves sending a probe to rendezvous with the next confirmed interstellar visitor, using ion propulsion and gravity assists to match velocities, deploying instruments to directly sample the object's composition. The European Space Agency announces its own program, the Biodetection Satellite Network, a constellation of 30 spacecraft positioned throughout the inner solar system, specifically to detect and characterize any passing objects. Each satellite carries spectrometers, cameras, and sample collection systems that can activate autonomously when sensors detect appropriate targets. The network aims to ensure that no future interstellar visitor goes unnoticed. No matter when or where it appears, China reveals plans for a permanent space station dedicated to monitoring incoming objects and serving as a staging point for rapid response missions. The Tiangong 4 station, as they're calling it, will maintain a crew of 6 scientists and pilots ready to launch intercept vehicles within hours of detecting a new arrival. We cannot allow another 3I Atlas to pass through our system without close study, the Chinese Space Agency's director declares. This is humanity's greatest opportunity to understand our place in a living universe. Private companies race to develop enabling technologies. SpaceX proposes rapid response spacecraft that can reach any point in the inner solar system within weeks. Blue Origin designs sample return capsules that can operate autonomously, collecting material from comets or asteroids without human intervention. Planetary Resources, pivoting from its original mission of asteroid mining, develops contamination-proof sample containers that maintain pristine vacuum conditions throughout collection and return. The biggest challenge isn't technology, it's safety. If we collect samples from 3I Atlas or similar objects, if we bring potentially living alien microorganisms back to Earth, what happens if they escape containment? What if they can survive in Earth's environment? What if they compete with Earth's ecosystems, spreading like an invasive species with no natural predators? The biosafety protocols read like science fiction. Any returning samples must be intercepted in space, transferred to secure containers without ever entering Earth's atmosphere. Analysis happens in orbit, inside specially designed laboratories, aboard the International Space Station or future dedicated research platforms. Only after thorough study, only after absolute certainty that the samples pose no threat, would they be allowed to reach Earth's surface, and even then, only to maximum containment facilities, similar to those used for studying the deadliest terrestrial pathogens. Some scientists argue for a permanent quarantine. Keep all extraterrestrial samples in space forever, they say. Study them remotely, use robots and automated systems, take no chances with Earth's biosphere. Others counter that we've been receiving alien organic material for billions of years through natural meteorite impacts. If dangerous life could hitchhike to Earth, it would have done so already. The risk of intentional sample return, they argue, is no greater than the risk we've always faced. Dr. Anderson's calculations address this question too. His model suggests that every square kilometer of Earth's surface receives approximately 1 gram of extraterrestrial organic material per million years. Multiply that by Earth's surface area over 4 billion years, and you get staggering numbers. Millions of tons of cosmic organic material have already rained down on our planet. Some burned up in the atmosphere. Some crashed into oceans. Some embedded in ice at the poles. Some fell on land, where erosion and geology eventually recycled them into Earth's crust. We're already living in a biologically interconnected solar system, Anderson argues. The question isn't whether alien microorganisms can reach Earth. They have, they do. They will continue to regardless of our actions. The question is whether we study this process systematically or remain ignorant of it. The philosophical aftershocks continue spreading through human culture. Humanity's cosmic loneliness ends, replaced by the knowledge that life pervades the galaxy at the most fundamental level. Our responsibility expands beyond stewardship of one world to recognizing our role in a living universe. Children growing up today will never experience the pre-3i Atlas worldview where Earth stood alone, where life was thought to be rare and precious and isolated. These children will assume life fills the cosmos. They'll assume that every star system probably hosts some form of biology, even if just dormant microorganisms in comets. They'll grow up knowing that when humans eventually travel to other stars, we'll likely find worlds already inhabited, already thriving with life that arrived long before us, carried on the same interstellar winds that might someday carry Earth's life to distant systems. The transformation extends to how we think about evolution and deep time. Darwin showed that all earthly life descends from common ancestors, that species change over generations through natural selection acting on random variation. But if life regularly arrives from space, if Earth's biosphere occasionally receives injections of alien genetic material, then evolution becomes more complex. Not just vertical inheritance from parent to offspring, but horizontal transfer from cosmos to planet, mixing genetic libraries from different worlds. Some organisms on Earth already do this. Bacteria exchange genetic material promiscuously through processes like horizontal gene transfer, swapping useful genes like humans share recipes. If alien microorganisms occasionally arrive on Earth, if some of them survive long enough to exchange genes with native bacteria, then Earth's genomes might contain sequences from other worlds. Fossil evidence of ancient contacts we never knew occurred. Genetic scientists immediately begin looking for such sequences. They search for genes that don't fit Earth's evolutionary tree, for stretches of DNA that appear suddenly in the fossil record without clear precursors, for biochemical processes that seem oddly out of place. It's early yet, but preliminary results suggest several candidate sequences. Genes that every statistician would say are outliers, that don't quite match the patterns we expect from ordinary evolution. One candidate sequence appears in certain extremophile bacteria that thrive in radioactive environments. The genes involved in their radiation resistance show unusual characteristics, codon usage that doesn't match other bacterial genes, protein structures that seem over-engineered for their function. Could these genes have arrived from elsewhere, perhaps aboard a radioactive meteorite, already optimized for handling radiation because they evolved on a world with higher background radiation than Earth? The implications for human identity become profound and personal. Every human carries about 37 trillion cells in their body. Those cells contain DNA, the genetic blueprint that makes us human. But we also carry about the same number of bacterial cells, mostly in our digestive system, organisms with their own DNA distinct from ours. If some of that bacterial DNA traces back to cosmic sources, to microorganisms that arrived on ancient comets, then we're literally made of stardust in ways more direct than poetic. More than that, the atoms in our bodies definitely come from space. Every carbon atom was forged in dying stars. Every oxygen atom came from fusion reactions in stellar cores. Every heavy element, from the iron in our blood to the calcium in our bones, formed in supernovae explosions billions of years ago. We are, quite literally, recycled star material organized into complex patterns that can think and wonder about their origins. But if the patterns themselves, the genetic instructions, the biochemical processes that organize those atoms into living cells, if those also came from space, arrived aboard comets, spread from world to world over billions of years, then we're not just made of cosmic material. We're products of a cosmic process, part of a living network that spans the galaxy, connected to alien organisms we'll never meet by shared ancestry more ancient than Earth itself. This knowledge changes how we see ourselves and our future. We're not preparing to bring life to a dead universe. We're joining a conversation that's been ongoing for billions of years. When humans eventually establish colonies on Mars, on the moons of Jupiter, on planets around other stars, we won't be alone. We'll be adding our chapter to a story that started long before us and will continue long after humanity is gone. The universe lives. It's been alive for billions of years. Life spreads, endures, adapts, fills every available niche through processes both violent and patient. And now, finally, one of those living worlds has evolved a species capable of understanding this truth, of seeing beyond the isolation of a single planet, to recognize the vast biological network connecting everything. We're not alone. We never were. We're part of something ancient and vast and ongoing, something that started when the first microorganisms survived the first planetary impacts and began the slow process of crossing the cosmic ocean. Something that continues today as comets like 3I Atlas sail through our solar system carrying passengers from distant homes. Something we're finally learning to see, to study, to understand. Tomorrow, we'll explore the theory of panspermia in detail, examining how life spreads between worlds and what that means for the origin of life on Earth. We'll look at the evidence that Earth itself might be a colony, that the first organisms on our planet might have arrived from elsewhere, that we might all be descendants of ancient cosmic travelers. But tonight, sit with this transformed understanding. The universe isn't a cold, dead place with rare islands of life scattered through infinite darkness. It's alive at every level, from the smallest microorganism to the largest structures. Life is the universe's way of organizing matter, of fighting entropy, of creating complexity and meaning and beauty. And we're part of that process, products of 4 billion years of evolution that might have started on another world and continued here, making us both Earthlings and cosmic citizens. The universe just got crowded, not with alien civilizations or flying saucers, but with the fundamental presence of life everywhere. And somehow that makes the cosmos feel less like a vast empty darkness and more like home. The theory of panspermia, life spreading between worlds like seeds on cosmic winds, transforms from fringe speculation to leading scientific paradigm almost. Overnight after the 3I Atlas discovery, the word itself comes from Greek, pan meaning all, spermia meaning seed. The idea that life seeds itself throughout the universe, that planets don't generate biology independently but receive it from elsewhere, has been around for over a century. But until now, it remained unprovable, unfalsifiable, more philosophy than science. 3I Atlas changes that. It provides the proof of concept, the demonstration that the mechanism works, that life really can cross the interstellar void. Evidence for this cosmic exchange has been mounting for decades, building a picture of a galaxy where life surfs gravity waves between stellar islands. We just didn't recognize what we were seeing until 3I Atlas made it obvious. Look at Earth's own history. The late heavy bombardment 4 billion years ago delivered thousands of tons of organic compounds to our young planet. We've known about this for decades. What we didn't know was whether those organic compounds were just simple chemistry or actual biological material. Meteorite, MH 4001, sits in a climate-controlled vault at NASA's Johnson Space Center in Houston. Scientists recovered it from Antarctica in 1984, but didn't realize what they had until 1996. Chemical analysis proved it came from Mars, ejected by an impact millions of years ago, drifting through space until Earth's gravity captured it. But the really interesting part was what researchers found inside. Tiny structures resembling fossilized bacteria. The discovery sparked fierce debate. Are they really fossils, or just mineral formations that happen to look biological? 28 years later, scientists still argue about it. But recent reanalysis using more sophisticated instruments suggests that at minimum, the meteorite contains complex organic molecules arranged in patterns consistent with biological processes. Whether it carried actual Martian life or just the chemical signatures of ancient Martian biology It proves that biological material can survive the journey from Mars to Earth. And if material can travel from Mars to Earth, it can travel from Earth to Mars, and from both planets to the moons of Jupiter, and from our solar system to other stellar systems. The physics doesn't care about direction. It's just gravity, velocity, and time. The Murchison meteorite, which fell in Australia in 1969, tells an even more remarkable story. Analysis found over 70 different amino acids in its pristine interior, including many that don't exist on Earth. 70 different amino acids. Earth's biology uses exactly 20. The other 50 in the meteorite represent chemistry that never occurred on our planet. Organic synthesis happening somewhere else. Perhaps in molecular clouds, perhaps on ancient asteroids, perhaps on worlds that no longer exist. These amino acids weren't contamination from Earth. Researchers took extreme precautions, analyzing the meteorite's interior within hours of its fall, using sterile techniques to prevent any terrestrial material from affecting the results. The amino acids were real, were extraterrestrial, were evidence that complex organic chemistry happens throughout the solar system and beyond. Each space rock that falls to Earth potentially carries microscopic passengers. Most burn up in the atmosphere. Friction with air molecules heating them to thousands of degrees, incinerating anything on their surface. But the interiors of larger meteorites can remain cool, protected by ablation, the outer layers burning away and carrying heat with them, leaving the core relatively undamaged. Simulations show that microorganisms embedded in rock a few centimeters below the surface can survive atmospheric entry without exposure to lethal temperatures. Dr. Chandra Wickramasinghe spent 50 years advocating for panspermia, while most of the scientific community dismissed him as overly optimistic, perhaps delusional. He's a professor at the University of Buckingham in England, trained in mathematics and astronomy, who built his career on the radical idea that life isn't rare, that it fills the galaxy, that Earth received its first organisms from space rather than generating them independently. For decades, he endured skepticism and criticism. His papers struggled to get published. Conference organizers relegated him to side sessions. Graduate students avoided working with him because association with panspermia theory could damage their careers. But Wickramasinghe persisted, accumulating evidence, refining calculations, demonstrating that the mathematics supported his conclusions even if the biology remained controversial. Now, watching 3I Atlas's discovery vindicate his life's work, he's gracious. "I never needed to be proven right," he says in an interview. "I just needed people to look at the evidence without prejudice." 3I Atlas forces that honest assessment. The mechanism exists, life travels. The question now is how often, not whether. His calculations show that microorganisms embedded in rock, ejected from Earth by asteroid impacts, could reach Mars in 3 years on average. The journey doesn't require millions of years when traveling between neighboring planets. Pieces of Earth launched by impacts follow elliptical orbits determined by the ejection velocity and angle. Many fall back to Earth, some crash into the Sun, but some achieve the right trajectory to encounter Mars when both planets happen to be in favorable positions. The math extends to more distant destinations. Jupiter's moons could receive Earth material in 12 years, Neptune in 45 years. Escape velocity from the solar system entirely, 58,000 miles per hour. Material traveling that fast, ejected by a particularly violent impact, could reach Proxima Centauri, the nearest star, in 45 million years. Could reach Wolf 359, 3I Atlas's probable origin, in 130 million years. That's much faster than 3I Atlas's journey because it assumes directed travel along the shortest path rather than the wandering trajectory that comets actually follow. But the point stands, life doesn't need spacecraft to cross between stars. It just needs violence, velocity, and time. All three exist in abundance throughout the galaxy. The mechanism works both ways. Earth sends its own microorganisms into space constantly. The Chicxulub impact that killed the dinosaurs 66 million years ago deposited a layer of iridium-rich rock around the planet, evidence of the asteroid's composition. But it also ejected millions of tons of terrestrial material beyond Earth's gravity well. Some of that material came from the ocean. Some came from forests. Some came from soil rich in microorganisms. Imagine the violence of that impact. An asteroid 6 miles across hitting Earth at 45,000 miles per hour. Energy equivalent to 100 million megatons of TNT. Rock vaporized instantly. Shockwaves racing through the planet's crust. Material thrown upward at velocities exceeding escape speed. In the first few seconds after impact, thousands of rocks containing Earth's microorganisms achieved trajectories that would carry them beyond the Moon. Beyond Mars, beyond the solar system entirely. Where are those rocks now? Some crashed into other planets in our system, potentially seeding them with Earth's biology. Some burned up in the sun. But some, perhaps millions of individual fragments, escaped into interstellar space. Right now, at this very moment, Earth bacteria from the dinosaur extinction event are arriving at distant stars, beginning the next chapter of their existence on alien worlds we'll never see. Laboratory simulations confirm the feasibility of this natural dispersal. Scientists place bacterial spores inside artificial rocks, subject them to impacts that simulate asteroid collisions, expose them to simulated interstellar conditions, radiation, vacuum, temperature extremes. The results consistently show survival rates of 20 to 40%. Not every organism survives, but enough do that even a small fragment of ejected planetary material likely carries living passengers, tardigrades. Those microscopic water bears we discussed earlier thrive in every torture scenario scientists devise. They've been frozen to near absolute zero, heated to 300 degrees Fahrenheit, compressed to pressures 6 times greater than the deepest ocean trenches, bombarded with radiation doses 1,000 times the lethal level for humans. They survive all of it. Return them to favorable conditions, and they rehydrate, resume normal activity, reproduce successfully. Some organisms don't just tolerate space conditions, they seem adapted for it. Certain bacterial spores show higher survival rates in vacuum than in air. Some repair DNA damage more efficiently under radiation exposure than without it, as if the radiation itself activates repair mechanisms. These traits didn't evolve for space travel specifically. They evolved on Earth for terrestrial challenges, but by coincidence, they're exactly the traits needed for interstellar journeys. This suggests something profound about life's nature. The strategies that allow organisms to survive extreme environments on Earth, Antarctic ice, deep ocean vents, radioactive waste sites, acid hot springs, are the same strategies needed to survive space. Life, in preparing for Earth's challenges, accidentally prepared itself for cosmic dispersal. Or perhaps not accidentally. Perhaps the ability to survive extreme conditions is so fundamental to life's success that any biology, anywhere, develops similar capabilities. The new paradigm sees solar systems not as isolated islands, but as connected neighborhoods, exchanging biological material constantly. Comets serve as public transportation, asteroids as cargo ships, stellar flares and impacts as launching mechanisms. Life adapts to local conditions after arrival, diverging into new forms, while maintaining core biochemical similarities inherited from the common ancestor that might have originated anywhere in the galaxy. This explains one of biology's deepest mysteries: why all Earth's life uses the same genetic code, the same 20 amino acids, the same molecular machinery. The traditional explanation is common descent from a single origin. All organisms descended from one ancestral cell that happened to use this particular code. But if Earth received its first life from space, if that delivery contained microorganisms already using this genetic system, then Earth's biochemical uniformity reflects not local origins, but cosmic inheritance. We're all immigrants, or descendants of immigrants. Or if Earth somehow generated its own life independently, only to be supplemented by later arrivals, we're hybrids. Mixed-breed organisms carrying genetic material from multiple sources, only some of which originated on this planet. Our cells might contain genes that evolved on Mars, on ancient asteroids, on worlds orbiting red dwarf stars in stellar systems we can't even see from Earth. DNA analysis might eventually reveal these mixed origins. Scientists are beginning to look for anomalies in the genetic record, for sequences that appear suddenly without clear evolutionary precursors, for genes that work perfectly but don't quite fit the pattern of gradual modification expected from Darwinian evolution. It's early in this research, but several candidates have emerged. Genes that seem over-engineered, more sophisticated than they need to be for their current function, as if they evolved elsewhere for different purposes and got repurposed on Earth. The implications for our cosmic future expand dramatically under this paradigm. When humans eventually establish permanent colonies on Mars, on Europa, on Titan, we won't just be settling new territory. We'll be participating in the same dispersal process that's been operating for billions of years. Will be life spreading from its current home to new worlds, using technology instead of impacts, but achieving the same result. And we might not be settling virgin territory. These worlds might already harbor life that arrived long before us, dormant beneath the ice or deep underground, waiting for conditions to improve. When we drill into Europa's subsurface ocean or excavate Martian caves, we might find cousins rather than empty real estate. Organisms that share our deepest biochemical ancestry because we all descended from the same cosmic seed, scattered across the solar system by impacts that occurred when the planets were young. This changes the ethics of space exploration. If life exists throughout the solar system, delivered by natural processes operating for billions of years, then planetary protection protocols take on new meaning. We're not protecting pristine environments from contamination. We're trying to avoid disrupting ecosystems that might be older than Earth's surface life, that might preserve biological lineages extinct everywhere else, that might represent unique evolutionary experiments conducted in isolation for billions of years. The search for life on Mars becomes more urgent and more complex. If we find microorganisms in Martian soil, are they native Martians, descended from organisms that evolved independently on the red planet? Or are they transplanted Earth life, delivered by meteorite impacts over billions of years? Or are they, like Earth's life, descended from common ancestors that seeded both planets when the solar system was young? Genetic analysis should answer these questions. If Martian organisms use the same genetic code as Earth's life, if their DNA shows clear evolutionary relationship to terrestrial organisms, that strongly suggests transfer from Earth to Mars or vice versa. If they use a completely different genetic system, different amino acids, different molecular machinery, that suggests independent origin. But if they show similarities but not identity, partial overlap in biochemistry, that might indicate common ancestry from a third source that seeded both worlds. Each possibility tells a different story about life's origins and dispersal. Each has profound implications for how common life is throughout the galaxy. If life originated independently on both Earth and Mars, two planets in the same solar system, then biology must be incredibly easy to start, probably existing on billions of worlds. If transfer occurred between them, that demonstrates panspermia on a local scale and suggests it happens on interstellar scales too. If both planets were seeded from elsewhere, that proves life's cosmic origin and raises questions about where the original source might have been. We're living through a transition in human understanding as profound as the Copernican revolution, when we learned that Earth orbits the Sun rather than the reverse. That discovery displaced Earth from the center of the universe, made it just another planet, undermined humanity's special status. The panspermia paradigm does something similar, but even more fundamental. It displaces Earth as the sole cradle of life, makes our planet just another recipient of cosmic biology, reveals humanity as part of a living network spanning the galaxy. But unlike the Copernican revolution, which made the universe seem larger and more impersonal, this discovery makes it feel more connected, more alive. We're not alone. We're part of something ancient and vast. Our very existence testifies to processes operating across billions of years and trillions of miles. Every cell in our body carries molecular machinery that might have originated on worlds we'll never see, refined by evolution that occurred before Earth existed. Tomorrow, we'll explore what all this means for humanity's future. We'll look at the missions being planned to catch the next interstellar visitor, to sample its cargo, to confirm definitively what we now suspect with high confidence. We'll examine how this discovery transforms our approach to searching for life and our plans for becoming a spacefaring civilization. But tonight, let yourself adjust to this new identity. You're not just human. You're not just Earthling. You're a cosmic organism, part of a living galaxy, connected through shared chemistry to every other form of life that exists or has ever existed anywhere in the universe. Your ancestors didn't just crawl out of the primordial soup. They sailed between stars, survived impossible journeys, persisted for billions of years, waiting for the right conditions to flourish. You're the product of the greatest migration in history. And the journey isn't over. It's just beginning to accelerate, as conscious life finally develops the tools to understand its own cosmic origins and participate deliberately in the spreading of biology across the galaxy. We're all aliens. We're all immigrants from space. We're all passengers on Spaceship Earth, but the ship itself is just one island in an archipelago connected by currents we're only beginning to map. And that makes the universe not smaller, but infinitely more interesting. Humanity stands at the threshold of the biological space age. Not the space age of rockets and satellites and moon landings. We've been living in that era for 70 years. This is something different, something that transforms our relationship with the cosmos from exploration to participation. We're about to become active members of the galaxy's living network, deliberately seeking out the biological cargo that's been sailing past us for billions of years. Most of it unnoticed, undetected, lost in the darkness. The Breakthrough Listen project, originally designed to search for radio signals from intelligent civilizations, announces a major pivot 3 weeks after the Three-Eye Atlas discovery. They're redirecting resources toward detecting biosignatures on passing objects. Instead of listening for deliberate messages, they're looking for the chemical signatures of life itself. The project's director, Dr. Andrew Simeon, explains the logic. We've been searching for civilizations, for intelligence, for technology. But Three-Eye Atlas suggests we should start with the fundamentals. Find life first in whatever form it takes. Intelligent life is a subset of that larger category. The technical challenge is immense. Interstellar objects move fast, appear without warning, remain visible for weeks or months before sailing back into the void. Traditional telescope scheduling, where astronomers compete for observation time months or years in advance, doesn't work. By the time you get approved for observations, the object is gone. What's needed is rapid response capability. Automated detection systems that can spot incoming visitors and immediately deploy appropriate instruments without human intervention. Universities create new departments of astrobiology almost overnight. Stanford launches its Center for Cosmic Life Studies. MIT establishes the Institute for Interstellar Biology. Cambridge, Oxford, Tokyo University, the Max Planck Institute, major research universities worldwide recognize this as a transformative moment and move quickly to position themselves at the frontier. Students flooding into these programs don't want to study abstract theories. They want to analyze real samples from real interstellar objects carrying real alien life. Investment pours into enabling technologies. The previous decade saw space companies focusing on satellite internet, space tourism, asteroid mining for metals and minerals. Now the economics shift toward biological prospecting. Venture capital funds the development of sophisticated spectrometers that can operate autonomously on small spacecraft. Engineering teams design sample collection systems that can grab material from passing comets without contaminating it or being contaminated by it. The space economy, worth approximately $400 billion annually by 2024, pivots dramatically. Launch providers see demand surge as research institutions and companies compete to deploy detection satellites. Spacecraft manufacturers retool assembly lines to produce bioprospecting vehicles. Even entertainment companies get involved, funding documentary missions to capture footage of humanity's first encounters with confirmed extraterrestrial life. The next interstellar visitor could arrive any time. Statistical models based on decades of observation suggest one passes through the inner solar system every 5 to 10 years on average. Most remain undetected, too small or too dark to spot with current instruments, arriving and departing without anyone noticing. But that's changing. New detection systems coming online will change our ability to see what's been invisible. The Vera Rubin Observatory in Chile represents the cutting edge of this new capability. Named for the astronomer who discovered evidence for dark matter, it features an 8.4-meter mirror and the largest digital camera ever built for astronomy, 3.2 billion pixels. When it begins full operations in 2025, it will photograph the entire visible sky every few nights, automatically detecting anything that moves, changes brightness, or appears where nothing existed before. Current systems can spot objects down to magnitude 24, meaning they can see things about 10 million times fainter than what the human eye can see. Vera Rubin will reach magnitude 27, 10 times fainter still. That sensitivity means detecting interstellar visitors weeks or even months earlier, when they're still in the outer solar system, providing extended observation windows and time to organize intercept missions. Early warning matters enormously. If we detect an object like 3I Atlas when it's still beyond Jupiter's orbit, we have months to reach it. Spacecraft launched from Earth can match trajectories, deploy instruments, collect samples. But if we don't spot it until it's already passing Mars, we get days or weeks, barely enough time to point telescopes at it before it's gone. The difference between months and weeks determines whether we can touch these visitors or just watch them pass. Mission concepts multiply in the aftermath of 3I Atlas. Project Lyra, developed by the Initiative for Interstellar Studies, envisions nuclear-powered probes fast enough to catch departing interstellar objects. The design uses nuclear electric propulsion to achieve velocities of 90,000 miles per hour, fast enough to chase down even the swiftest cosmic visitors. The mission profile involves launching the probe toward the object's projected path, matching velocities, and accompanying it for months while collecting data. The Comet Life Detection Array represents a different approach. Instead of chasing individual objects, this proposal distributes sensors throughout the solar system, creating a network that any passing visitor must transit. 30 spacecraft positioned in orbits from Venus to Jupiter, each carrying spectrometers, cameras, and sample collection devices. When an interstellar object appears, the nearest spacecraft activates, providing close-up study without requiring rapid response launches. Most ambitious is the Interstellar Sample Return mission, currently in preliminary design at NASA's Jet Propulsion Laboratory. The concept uses ion propulsion, the most efficient rocket technology available to chase down objects and return physical samples to Earth orbit. The mission would take years, launch, intercept, collection, return journey, but would provide the first laboratory analysis of confirmed interstellar biological material. The technical challenges are enormous, the costs astronomical, but the scientific payoff justifies the investment. Public participation explodes beyond anything seen in previous space endeavors. The Planetary Society launches Comets Alive, a citizen science project coordinating global amateur observations of 3I Atlas and future visitors. Within weeks, 75,000 people sign up, ranging from professional astronomers with university-grade equipment to enthusiastic beginners with department store telescopes. The project provides coordination, scheduling, analysis tools, turning thousands of individual observers into a single distributed instrument. Your backyard telescope might spot the next life-bearing visitor. It's not just possible, it's probable. Amateur astronomers discover more comets than professionals because there are more amateurs, more telescopes, more sky being watched simultaneously. Peter Williams' initial detection of 3I Atlas's 17-hour pulse came from a 12-inch telescope in his backyard in New Zealand. The next discovery might come from someone's roof in suburban Ohio, a balcony in Tokyo, a field in rural Kenya. Educational systems scramble to prepare the next generation for this transformed reality. High school curricula add sections on astrobiology, interstellar chemistry, panspermia theory. College astronomy courses that previously spent one lecture on exoplanets and the search for life now dedicate entire semesters to biosignature detection and interstellar biology. Medical schools begin offering electives on xenobiology, preparing doctors for a future where human patients might carry microorganisms of extraterrestrial origin. The cultural transformation accelerates beyond institutional responses. Science fiction, which spent decades imagining first contact with intelligent aliens, pivots towards stories about encounters with microscopic life, about the implications of cosmic panspermia, about humanity's place in a living galaxy. Artists create works inspired by 3I Atlas's blue-green glow, by the romance of life crossing the void, by the discovery that we're connected to organisms we'll never meet on worlds we'll never see. Religious institutions continue processing the implications. The Vatican convenes a special symposium on extraterrestrial life and theological meaning. Islamic scholars examine hadith and Quranic verses that might reference life beyond Earth. Hindu teachers note that their tradition has always assumed countless worlds with countless forms of life. Buddhist retreats incorporate meditation on cosmic interconnection and the illusion of separation between terrestrial and extraterrestrial life, but perhaps the most profound transformation occurs in how children understand their world. Kids born after the 3I Atlas discovery will never experience the isolation previous generations assumed. They'll grow up knowing that life pervades the galaxy, that organisms travel between stars, that Earth participates in a cosmic ecosystem billions of years old. When they look at the night sky, they won't see dead vacuum punctuated by rare oases. They'll see a living network, a biological web connecting everything. These children will ask different questions than their parents asked. Not are we alone, but how many others are there? Not could life exist elsewhere, but which worlds host life and which don't? Not will we ever find aliens, but when will we meet our cosmic cousins? The shift from possibility to certainty, from hoping to knowing, transforms the human relationship with the universe. The future unfolds in ways science fiction never quite imagined. No alien invasions, no radio messages from distant civilizations announcing their presence. No flying saucers landing on the White House lawn. Instead, quiet confirmation that life permeates the universe at its most fundamental level. Microorganisms sailing between stars. Comets carrying biological cargo. Planets seeding each other through natural processes operating for billions of years. This future involves microscopes more than telescopes, spectrometers more than radio dishes, molecular biology more than radio astronomy. The search for life becomes the study of life, shifting from abstract possibility to concrete investigation. We're not wondering whether extraterrestrial organisms exist. We're examining them, sequencing their genes, comparing their biochemistry to ours, tracing their evolutionary history through chemical signatures preserved in ice. Every comet becomes potentially interesting. Every asteroid might harbor dormant passengers. Every meteorite that falls to Earth could contain traces of alien biology, fragments of organisms from worlds we can't see, evidence of the cosmic dispersal process that connects all living things. The distinction between terrestrial and extraterrestrial biology blurs until it becomes meaningless. Life is life, wherever it originated, whatever world it currently inhabits. The practical applications extend beyond pure science. Understanding how organisms survive extreme conditions, how they repair radiation damage, how they remain viable for millions of years, these insights revolutionize medicine, agriculture, and biotechnology. The antifreeze proteins that protect comet organisms from ice crystal damage might preserve human organs for transplantation. The DNA repair mechanisms could inform cancer treatments. The cryptobiosis strategies might enable long-duration space missions with humans in suspended animation. We're not conquering space in the old colonial sense. We're joining it, joining a process that's been ongoing since the first planetary systems formed, since the first organisms developed the resilience to survive cosmic dispersal, since life began its slow spread from world to world. Earth's children prepare to meet their relatives scattered among the stars, relatives who share our deepest biochemical ancestry. Even if we evolved on different worlds under different suns, the greatest adventure in human history begins, not with rockets and spacesuits, but with microscopes and spectrometers. Discovering that we've never been alone, that we've been part of something larger all along without realizing it. The universe lives, not metaphorically, not poetically, but literally and physically. Life exists on scales from microscopic to galactic, from single cells to planet-spanning ecosystems, potentially connected by biological networks we're only beginning to recognize. I-Atlas represents the beginning, not the end. One confirmed interstellar visitor carrying biological cargo, the first of thousands we'll detect over coming decades, each one a messenger from distant systems, each carrying information about conditions on other worlds, each contributing to our understanding of how life originates, spreads, and persists throughout the galaxy. The comet continues its journey through our solar system. Its closest approach to Earth occurs in January 2025, passing within 50 million miles, close enough for detailed study, but far enough to pose no danger. Telescopes track it continuously. Spacecraft prepare to intercept it. Scientists worldwide collaborate on observation plans. And somewhere, dormant microorganisms that survived a 4 million year journey briefly stir as warmth from our sun penetrates their icy home. Whether those particular organisms will seed Earth or another planet in our system remains unknown. Whether they'll find conditions suitable for active metabolism, for growth, for reproduction, we can't predict. But their presence proves the concept. Life crosses the void. Life endures the impossible. Life waits with patience beyond human comprehension for its next opportunity to flourish. As 3I Atlas departs, sailing back into the interstellar darkness from which it came, it leaves humanity transformed. We understand ourselves differently. We understand our planet differently. We understand the universe differently. The change isn't subtle. It's fundamental. We're not isolated. We're not alone. We're part of something ancient and vast and ongoing, and this is just the beginning. The biological space age, the era of actively seeking and studying extraterrestrial life at its most fundamental level, has only just started. Future generations will look back at this moment, at the discovery of 3I Atlas, as the turning point when humanity stopped wondering and started knowing. When we recognized that life's story isn't confined to one world, but spans the galaxy. When we accepted our role, not as life's sole custodians, but as one branch of a cosmic family, the universe lives. It's been alive for billions of years. Life spreads, endures, adapts, fills every available niche through processes both violent and patient. And we're finally learning to see it, to study it, to understand our place within it. not as conquerors or explorers of dead territory, but as participants in a living system that connects everything that has ever lived or will ever live anywhere in the cosmos. The harvest has begun, not of minerals or metals or energy, but of knowledge, of understanding, of recognition that we share this universe with countless other forms of life. Some intelligent, perhaps, some technological, maybe, but all alive, all connected through shared chemistry and shared history, all part of the same cosmic story that started billions of years ago and continues today. Tomorrow never ends in science. Each answer generates new questions. Each discovery reveals new mysteries. Each step forward opens new horizons. But we take this step knowing something profound and true. The universe isn't empty. It's full of life, waiting to be found, ready to teach us about ourselves and our origins and our future. We're all passengers on comets sailing through space and time. Some of those comets are made of rock and ice. Some are made of metal and dreams. But all carry the same cargo, life seeking new homes, spreading through the galaxy, connecting everything in ways we're only beginning to understand. The journey continues. And now, finally, we're conscious participants rather than ignorant passengers. We're learning to read the signs, to recognize our cosmic family, to understand that every atom in our bodies, every gene in our cells, every thought in our minds connects us to something larger than ourselves, larger than Earth, larger than anything we previously imagined. The universe just revealed one of its greatest secrets. And like all truly profound secrets, it changes everything while explaining what was always there, waiting to be seen.